Let's look at the tutorial on non-permanent joints. For question 1, it says that find the power required to drive a 40 mm power screw which is double threaded and the pitch is given as 6 mm. The nut is to move at a speed of 48 mm per second and it is to move a load of 10 kilonewton. The frictional coefficients is 0.1 for the thread and 0.15 for the collar, and the frictional diameter of the collar is given as 60 mm. So the pitch is given as 6 mm. The lead is basically N times P. N is indicating the type of thread, whether it's a single thread, double thread. So in this case it's a double thread, so N becomes 2. So 2 times your pitch, which was 6, we get our lead to be 12 mm. The mean diameter of the thread is simply given as the maximum diameter, which was given in the problem as 40 mm. So 40 mm minus half the pitch, which is P upon 2. So 40 minus 3 is 37. So that's your mean diameter. F is the coefficient of friction of the thread, Fc is the coefficient of friction of the collar, and dc is the frictional diameter of the collar, which was 60 mm. The load was given as 10 kilonewton. So the torque required to raise the load is given as such: F dm divided by 2 into L plus pi F dm divided by pi dm minus Fl. And then this takes into account the torque due to the collar that is introduced. So substituting for these values, so load was given as 10 kilonewton, so 10,000. The mean diameter of the thread was 37 mm, converting that to meters. The lead was 12 mm, everything is converted to meters, times plus pi into friction for the thread was 0.1. So substituting these values, and then coefficient of friction for the collar was 0.15. The frictional diameter of the collar was 60 mm, converting it to meters. So substituting for these values into the equation, we obtain that the torque required to raise the load is nothing but 82.95 Newton meter. Now we have to calculate the power as well, and power is simply given by the raising torque times the angular velocity at which the thread is rotating. So what happens is, in the question we given the velocity at which the thread is moving. It is simply given as 48 mm per second. So it moves a distance of 48 mm. It moves a distance of 48 mm every second, and we know that the lead for this screw is 12 mm. So what lead simply indicates is, lead is the distance that the nut moves for every complete turn, for every one turn of the thread. So what happens is, the velocity was given as 48 mm per second, the lead was given as 12 mm. So what we have is, the lead is 12 mm, so there's the distance that it moves every second. So 48 divided by 12, we simply get that the speed at which the thread is moving is 4 revolutions per second. Since the velocity was given per second, so it's per second, so the thread makes 4 turns every second. So when we calculate our power is TR upon TR, the torque required to raise the load, times your angular velocity, so which is simply TR times 2 pi. And you'll see that here you've got a small n, because small n indicates revolutions per second, right? We don't have to divide this by 60, so 82.95 times 2 pi times n was 4 revolutions per second. So we obtain that the power transmitted by this thread is simply 2084.76 watt. Let's look at question 2, which is looking at bolts in shear. So as the schematic shows, that a load of 20 kilonewton is acting. You've got a bolt pattern over here, and you've got 5 bolts, A, B, C, D and E. When you look at the configuration that is given to you, you can simply say that the centroid of the bolt pattern is right on E. So bolt E is right at the centroid of this bolt pattern. The distance at which the force is acting from the centroid, so this is your centroid O. So the distance DC, is basically 750 plus 50 plus 100. So the distance at which the force is acting from the centroid then simply equates to 900 mm. You have to calculate the resultant force acting on each bolt. We have to find the maximum shearing stress as well as the maximum bearing stress for this particular problem, and we are using M12 bolts. So basically the diameter of the bolts is 12 mm. So let's start. With respect to the bolt pattern, we can calculate the distance of all these bolts. So bolt A, the distance of bolt A from the centroid at O. So what happens is bolt E is right at the centroid. So we'll calculate the radius of bolt A, or the distance of bolt A from the centroid. So which is basically in the horizontal direction it is 100 mm, in the vertical direction from your centroid it is 100 mm. So the radius or the distance of bolt A from the centroid is basically 100 squared plus 100 squared, which simply equates to 141.42 mm. Since when you look at the bolt pattern, you'll see that bolt B, C and D are also located at the same distance from the centroid as bolt A. So therefore RA, RB, RC and RD are going to be same, which is 141.42 mm. When you look at bolt E is right at the centroid. So the distance of bolt E from the centroid is 0. So therefore RE is 0. The moment about this bolt pattern, the load was 20 kilonewton, and the distance of this force from the centroid over here is simply 900. 750 plus 50 plus 100, which is 900 mm. So the moment about this centroid is 18 kilonewton meter. The next thing that we can calculate is we can calculate the primary shear. Primary shear is basically the load divided by the number of bolts. So the load was 20 kilonewton divided by 5. Number of bolts were 5. So A, B, C, D, E. So your primary shear is 4 kilonewton. Now what we can do is we can calculate the secondary shear acting on bolt A. So this is bolt A. So your secondary shear on bolt A is given as basically M into Rn divided by Ra squared plus Rb squared plus Rc squared plus Rt squared plus Re squared. So since we're looking at the secondary shear on bolt A, so the distance becomes Ra over here. Now what happens is your moment is 18 kilonewton meter. The distance Ra, which is the distance of bolt A from the centroid, is basically 141.42 mm as calculated over here. So converting that to meters. Now what happens is when you look at your denominator, Re is simply 0 because the distance of bolt E from the centroid is 0, so this disappears. And then what happens is Ra, Rb, Rc and Rd have the same value. So basically what happens is we have 4 times Ra squared, because distance of the bolts from the centroid for A, B, C and D are same. So 4 times 141.42 times the power of -3 whole thing squared, and we obtain a value of 31.82 kilonewton as your secondary shear acting on bolt A. But since bolts B, C and D and I are located at same distance from the centroid O, so secondary shear on B, C, D is going to be same, which is going to be 31.82 kilonewton. Secondary shear on bolt E is going to be 0 because distance of bolt E from the centroid is 0. So in this equation, when you have 0, everything becomes 0. So secondary shear acting on bolt E is 0. The next thing is what we'll do is we'll look at the resultant forces acting in all the bolts. So when we look at bolt E, secondary shear was 0 because bolt E is at the centroid. So the only thing is you've got your primary shear, and your primary shear was simply 4 kilonewton. So the resultant force on bolt E is 4 kilonewton. The next thing is let's look at the resultant force acting on bolt I. So what happens is, looking at the bolt pattern, we need to calculate this angle over here, which is given as alpha. So alpha is tan inverse of basically opposite over adjacent. So opposite was 100 mm, adjacent was 100 mm. So basically your alpha is 45 degrees. So to find the resultant, which is over here, the resultant is over here. So what we do is we use the cosine rule. So fi squared is equals to f prime a squared plus f double prime a squared minus 2 f prime a times f double prime a cos theta. So what happens is your primary shear was 4 kilonewton, your secondary shear was 31.82 kilonewton. So 4 squared plus 31.82 squared minus 2 into 4 times 31.82 kilonewton times cos theta. When you look at this theta over here, this theta is basically 135, because what happens is when you look at this is 90 degrees over here, so this becomes 45 degrees. So basically what happens is when you look at this, from here to here is 180 degrees, and then we need to find what this angle is over here. So 180 is there. When you look at this angle over here, so this is 45, so this will be 45 as well. So basically 360 into 180, 360 minus 180 plus alpha, so you get your theta to be 135 degrees. So you can find this angle theta in so many ways, so whichever way is easier for you, you can use that. So we find that your resultant force acting on bolt A is given as 34.76 kilonewton. And when we look at the geometry, we'll say that the force acting on bolt A is same as the resultant force acting on bolt B. Now the next thing is when we look at bolt D. So for bolt D, we're just isolating the free body diagram that we got over here. So what happens is, how do we draw this free body diagram as explains in your lectures. So primary shear always acts in the same direction as your applied load, so it is acting downwards. Then what happens is we represent secondary shear on this lever arm such that it provides you with the same moment. So your global moment was clockwise over here, so global moment is clockwise about your centroid. So over here your moment should be clockwise as well. So the only way your secondary shear can cause a moment in the clockwise direction is if your secondary shear is acting in this direction. Same thing on the opposite side, it can only be in this direction. So that's again, so your secondary shear has to be represented at 90 degrees with respect to the distance of bolt D from your centroid. Again same thing for bolt B. When you look at bolt A, again this is how your secondary shear can only act to cause a moment in the clockwise direction about your centroid O. So when you look at this bolt pattern and the forces, you'll see that resultant force on A is same as resultant force on B, and resultant force on C and D is going to be exactly the same. So next thing is we can find this angle alpha, which is again 45 degrees. So resultant force on bolt D is FD squared is equals to this particular formula. So in this case when we look at it, theta is over here and then your resultant is in this direction, and then theta over here is basically 45 degrees, because you can do two things. This is 90 degrees over here, so this value is going to be 45, and then what happens is this again forms a 45 degrees over here, so therefore 45, so this theta is 45 degrees. So substituting for these variables in the equation over here, you simply get that your FD, the resultant force acting on bolt D, is 29.13 kilonewton. Again the force acting on bolt D is same as the force acting on bolt C with respect to the free body diagram representing the forces acting on these individual bolts. So now what happens is we'll calculate the maximum shear stress. So maximum shear stress is simply given as the F max divided by the cross-sectional area of the bolt. So this is what actually happened. The cross-sectional area of a bolt is a circle, and the maximum force acting was simply 34.76 kilonewton, which was acting on bolt I and bolt B. So this is your F max divided by the cross-sectional area, which is pi d squared upon 4. So the diameter of the bolt was 12 mm. So we obtain the maximum shear stress to be 307.35 megapascal. Now when we look at the bearing stress, the bearing stress is F max divided by bearing area. So the bearing area is simply given over here. So it is simply diameter times the thickness of